Today's topic will be industrial applications of electrolysis. Now, the objectives that will be covered in this topic will include to describe the industrial applications of electrolysis, and we will make reference to metallic extraction, purification, electroplating, and anodizing. Let us begin. Let's talk a little about metals and where they are found in their natural state. So you'll see that metals are found in the earth crust, and they are found as ores, O-R-E-S. An ore is a metal compound mixed with impurities. So we have our metal found in its natural state in the environment along with impurities. So we need to extract this metal from the ore and purify it. So when metals are removed from the earth crust, they must be separated from their compounds and the impurities. This is the whole process of extraction. Now we will be studying the extraction of sodium from brine, as well as the extraction of iron from iron oxides. Now this topic will be done in section C of the syllabus. For now, we are just interested in the principles behind the extraction process. So the method used to extract metals from their ores depend on the position. Very important. The position of the metal in the reactivity series. So you'll find out that some metals are high in the series, some are low in the series. Depending on where you are found in the series will determine your method of extraction. So the more reactive metals, and those are found at the top of the series, they are more difficult to extract. And those that are lower in the series are more easy to extract. You'll remember that those that are found way down in the bottom of the series will not form compounds, so there's no need to extract them from their compounds because they are found in their free state, their elemental state in the environment. Let us look at the method of extracting a metal based on where it is found in the reactivity series. As long as you are extracting a metal from its compound, the process is reduction. Now there are two types of reduction that we are going to look at. We are going to look at electrolytic reduction and reduction using a reducing agent. Now this is based on where you're found in the series. Now let's talk about the first one, electrolytic reduction. Now the process of electrolysis is a very powerful method used to extract metals from their compounds. That is to separate the metal from the non-metal. Remember that the metal and the non-metal are bonded strongly through very strong ionic bonds. So the very powerful method of electrolysis, this method is the best method to separate the ions. Now, when do you use electrolytic reduction to separate your metals? Look here at our reactivity series. Let us use iron as our reference point. The metals that are found above iron, these metals, they form stable compounds. And when I say stable compounds, I mean that the compounds that they form, they are very difficult to separate. Hence, the bonds are very strong. Hence, we say that they are stable. Now, from iron down, these compounds now, they form what? Less stable compounds. Now, these compounds that are formed from iron down, they are more easily separated than the ones above in the reactivity series. So the ones above form very stable compounds. The ones below from iron down form less stable compounds. So the process used to separate those that are above iron is electrolytic reduction, which is really electrolysis, where You'll have your cathode and your anode, and your metal compound would be molten or aqueous, and that will be your electrolyte, which the metal, being positive, will move towards the cathode. And remember that the process that takes place at the cathode is that electrons will be gained. And if electrons are gained at the cathode, then reduction takes place, hence electrolytic reduction. Let us take a look at this simulation.
A graphic illustration of the extraction of aluminium is shown. A mixture of powdered alumina, cryolite and fluorspar is carried by a conveyor belt and charged in the electrolytic vessel. Carbon rods act as the anode, and the thick graphite-lined vessel acts as the cathode. Cryolite and fluorspar are used to lower the melting temperature and increase conductivity. A temperature of 900 degrees Celsius is maintained inside the electrolytic vessel. Alumina splits into the aluminium ion and oxide ion. At the cathode, the aluminium ions gain electrons and get reduced to aluminium. At the anode, the oxide ion loses electrons and is oxidized into an oxygen atom. At 900 degrees Celsius, oxygen gas combines with the graphite anode to form carbon dioxide, causing the size of the anode to decrease. Hence, it must be changed periodically. The molten aluminium collects at the bottom of the vessel and is tapped out. In a membrane cell, an ion exchange membrane separates the anode and cathode compartments. The separator is generally a bilayer membrane made of perfluorocarboxylic acid between the anode and the cathode. The saturated brine is fed to the anode compartment. Chlorine is liberated at the anode, and the sodium ions migrate to the cathode compartment. Hydrogen gas, saturated with water, exits from the cathodic compartment. The unreacted sodium chloride and other inert ions remain in solution. About 30 to 32% caustic soda is fed to the cathode compartment, where sodium ions react with hydroxyl ions produced by hydrogen evolution at anode from the water molecules. This forms caustic soda, which increases the concentration of caustic solution to approximately 35%. Hydrogen gas is formed at the cathode. Hydrogen is usually burnt at the electrolysis plant to provide thermal energy to evaporate water from the sodium hydroxide solution.
Those below, from iron down, for example, your iron 3 oxide, and so on, these now will be separated using a reducing agent. So the process is reduction using a reducing agent. Now, what's an example of a very good reducing agent? Well, carbon is normally used, but carbon in the form of carbon monoxide or carbon dioxide. These are very good reducing agents. So carbon is solid. So being solid, it will not work as effective as if it is in the gaseous state where carbon monoxide is, or carbon dioxide. So the reducing agent is really carbon, but it is oxidized to form carbon monoxide or carbon dioxide, and these are more effective reducing agents than carbon solid itself. So just remember now, all we need to know is that those above iron are separated from their compounds by electrolytic reduction, electrolysis, because they form highly stable compounds. Those below, they are separated using a less powerful method called reduction using a reducing agent because they form less stable compounds. What are some examples of a compound that can be separated using electrolysis, or an example of a compound that can be separated by a reducing agent? Let's look at sodium chloride. Sodium chloride, as you can see, sodium is found high in the series. So sodium chloride is a very stable compound. Being very stable, the process then would be electrolytic reduction. In the case of iron 3 oxide, the process to separate this one would be reduction using a reducing agent, because this compound is not so stable. So this compound is less stable because it is found lower down the series. So less stable. To separate iron from iron 3 oxide, we must use now reduction using a reducing agent. So basically, any compound you get, and they say, what is the best method to separate that element or metal from its compound, you must identify its location in the reactivity series. If it is high in the series, then the method would be electrolytic reduction, which is really electrolysis. If the metal is found lower in the series, then that method would now be reduction using a reducing agent, which is carbon in the form of carbon monoxide or carbon dioxide. And again, we say that the gaseous form of carbon are more effective reducing agent than the solid form of carbon. Let us take a look at this simulation.
Iron. The chief ore of iron is hematite, Fe2O3. The charge, hematite, limestone and coke, is fed into the blast furnace. A blast of very hot air is injected near the bottom of the furnace. Coke burns to form CO2, which reacts with more coke to form carbon monoxide, CO. CO reduces the ore to molten iron, which collects at the bottom of the furnace. Silica, SiO2, an impurity, combines with the limestone to form slag, which floats at the top. Molten iron and slag can be tapped separately.
Let us move on to another industrial application of electrolysis, and this method will be purification. So after you've extracted your metal from its ore, we need to purify that metal. Now, most metals are impure, thus they need to be purified. Now, the presence of impurities will affect the properties of a metal. It will either decrease the conductivity or make the metal more brittle. So, purifying your metal is very important. Based on what was done already in the process of electrolysis, you would know that we must put our impure copper, using copper as our example, our impure copper must be placed at the anode, which is the positive electrode. Now, the positive electrode is the anode and the negative electrode is the cathode. The impure copper being placed at the anode will make this type of electrolysis an active one, because our electrolyte is going to be a salt of the metal at the anode. So copper 2 sulfate is our electrolyte, while copper is placed at the anode. Hence, being an active electrode, we're going to have dissolving of our metal taking place. So the copper that is impure placed at the anode will dissolve and move from your atom to your ion. Once you form your ion, the impurities that are present in the metal will fall off into the container as sludge. Then the ions that were formed in the solution will be reduced by gaining electrons to form a solid at the cathode. So you'll notice that the impure copper at the anode dissolves, breaks down into ions, and then at the cathode, the ions gain electrons and form back your copper solid. As you can notice here, you'll see that the cathode is getting bigger in size because copper is being formed around it. So at the anode, you have a breakdown of your solid to ions, while at the cathode, you have a buildup of your solid from ions. And this explains the process of purification. Point to note, any metal that you are purifying must be the active electrode, which means it must be placed at the anode so it can dissolve into the electrolyte, leaving or dropping off the impurities. Then the ions will be reduced at the cathode, forming a solid of a pure metal. So this explains the process of purification. Let's look at the process of electroplating, which is of a very similar principle, but only different in the name of purification and electroplating. Now, in electroplating, all we're doing is coating one object with a thin layer of another metal. So in this case, we are coating this metal object, which is a spoon, with silver metal. So whatever we are coating must be placed at the cathode. So you can see that this being the short side of the power source is the cathode. So the object being plated is placed at the cathode, and the object or the metal doing the plating is placed at the anode. Again, remember that the anode is the active electrode. So on this side is our positive electrode being the anode, and on this side we'll have the cathode. So if our metal doing the coating is placed at the anode, that metal will be dissolved, forming ions. So you'll see where silver solid will be oxidized at the anode to form silver ion. And the ions will now gain electrons at the cathode to form silver solid. And this silver solid is what is formed around the spoon where reduction took place. So reduction at the cathode, while oxidation took place at the anode. So the silver will dissolve, forming silver ions, and those silver ions will be built up as they are being reduced around the metal spoon. Since this is an example of an active electrode, then the electrolyte must be a soluble salt of silver. In this case, we use silver nitrate as the soluble salt. So as you can see, this is very similar to the process of purification, where the impure substance is placed at the anode and the pure substance is placed at the cathode. In this case, what I want to dissolve, I put at the anode, and it is built up around the cathode. And that is the process of electroplating. So let's look at another example. Suppose we want to electroplate a chain, and that chain might be silver or a piece of wire, and we want to electroplate that wire chain or silver chain with gold. Then that chain must be placed at the cathode, while the gold is placed at the anode. We must use gold nitrate as our electrolyte because it is active. So the gold would dissolve to form gold ions, and the gold ions will now be reduced at the cathode, forming around the chain. We would then take out the chain after we ensured that it was properly cleaned, fully immersed into the electrolyte, and that the time that the electrolysis process was run for is adequate or sufficient to get the gold properly around the chain. after which we would remove it and sand it down to make it shiny. And that is our process of electroplating. So you pretty much can electroplate any metal you want to electroplate with another metal by following this process. Let us take a look at this simulation.
In electroplating, the anode is a metal present in the electrolyte. The anode is a block of pure metal to be used for coating. The electrolyte is a solution of a salt of the coating metal. The object to be coated is made the cathode, since metal ions being positively charged are attracted to the cathode. The object must be very clean and free of grease. The object to be coated must be rotated for even coating. The temperature, the concentration of the electrolyte and the current must be controlled so that the layer does not form too fast, as otherwise it will flake off.
Let's look at the final industrial application of electrolysis, and that process is anodizing. Now, please don't get confused with this process of anodizing. Understand that anodizing is a process by which a coating of an oxide is placed around a metal. Now, in the case of an object like aluminum, this will cause the oxide to be formed, and this oxide would now be resistant to corrosion. So in terms of our electrolytic cell or setup, where do we put what? Now, let's identify our anode. And our anode will be on this side of the cell. That's our positive electrode, that's the anode. And that would now be our negative electrode, which is the cathode. Notice that in anodizing, whatever we are anodizing, whatever we want to coat with a layer of an oxide, that is what we place at the anode. So the anode is on this side here, and the cathode is on this side. Notice that the cathode is inert, carbon, graphite, platinum, inert cathode. The object being coated with oxygen is placed at the anode. Now why? That is where OH minus would migrate towards, because OH minus is negative, so it will migrate towards the positive electrode. OH minus will produce oxygen. Thus, oxygen would come off at the anode, coating the object with a layer of oxide. And that would be your protective layer around the aluminum. Now, what is our best electrolyte to use in the anodizing process? Well, any dilute acid could be used. So I could use HCl, or I could use H2SO4. And notice that these acids must be dilute. Now, why dilute acids? Well, the acid is dilute because our ions that are present will have OH minus present also. Now, being dilute, the position of the OH minus ions would take preference to the other ions. Hence, OH minus would produce water and oxygen. And this equation you know already. So this is the oxygen that is produced at the anode. And where did this oxygen come from? It came from the hydroxide ion, which came from an electrolyte that is a dilute acid. So we should understand that we must use a dilute acid for our electrolyte, and the object we want to coat with the oxygen, this time it must be placed at the anode, and the cathode must be inert. So you see that we want to coat this aluminum object with oxygen to form aluminum oxide, and that oxide will increase the resistance to corrosion. Now we have other types of corrosion. Do you remember the corrosion we call rust? Let's look at the oxide of iron and compare it with the oxide of aluminum and discuss the difference between the two. Let's look at the corrosion of iron. So iron, when it's corroded, would form iron 3 oxide. And corrosion of aluminum will form aluminum oxide. Now these two metals, iron and aluminum, underwent the process of corrosion. But this process here for iron is called rust or rusting. Now, what is the difference between the oxide of iron and the oxide of aluminum? Well, the oxide of iron will flake. And if it flakes, it will expose the inner surface of the metal to more corrosion. Hence, the metal will be eaten away slowly. Whereas the oxide of aluminum, it forms a protective layer. So you see, the oxide of aluminum will protect the metal, while the oxide of iron does not protect the metal. The main difference is one is flaky and the other one is not flaky and sticks to the metal and protects it. So the difference between the two is in the type of oxide that is produced and the flakiness that will occur in the oxide, exposing the metal in the case of iron, while the oxide of aluminum forms a thin protective layer around the aluminum, preventing any other form of corrosion from taking place. So this concludes another of our lessons in our chemistry lecture series. The next time we meet, we will be doing calculations involving Faraday's laws. See you then.